Mr. McLaurin, all right, he took the idea of Taylor polynomials and focused his study, okay? Taylor could do a polynomial centered anywhere you want, right? Centered at any position, you just added the x minus part and you were working on it. Maclaurin just really focused on a subset of Taylor polynomials that were always centered just at 0. So that made everything nice and clean. All right, so that's sort of the definition. And we use them so often that we call them by his name. All right, a Maclaurin polynomial is basically a Taylor polynomial centered at 0. So the interval of convergence is centered at 0. Everything's emanating from 0. Okay. We've done several of these already. They could be classified as Maclaurin. It is not new. All right, there are some polynomials that centered at 0, Maclaurin polynomials. Let me back up. You could generate a polynomial from scratch every single time, right? You could take the time, the tedious time, to figure out the derivatives, and then divide by the factorials, and then set it up, and you could come up with it. You could. However, it will be in your best interest to memorize some of the common ones. It's going to save you time, that you just recognize it. It's like the unit circle, right? You could figure out the unit circle every single time by like mentally doing the math and using the Pythagorean theorem, and it's possible to figure it out if you forget. But once you memorize the unit circle, it does make answering questions a lot faster. So same thing is true for here. So you'll probably want, we're going to make a couple flashcards to help us remember the ones that are the most common. All right, the first two are the most common trig ones. Okay. The following polynomial that starts with 1 and then minus u squared over 2 factorial plus u4 over 4 factorial minus u6 over 6 factorial plus u8 over 8 factorial. Do you see the pattern? Okay. What is the pattern of the powers? They're all even. The pattern of the factorials? All even. Would that pattern fit with the first term? Could I replace 1? It would be u0 over 0 factorial. So it would totally work. Plus, what else is changing every time? The sign is changing. Okay. This polynomial is the approximation for cosine. Yep. If you made a Taylor polynomial centered at 0. We did it for sine yesterday in our notes. We did sine. Remember when we did all the derivatives of sine, and it was like, okay, sine, cosine, negative cosine. It was 1, 0, negative 1, 0. And we did it. We created. Cosine comes out to be this. Okay? You should memorize this. And this is a memory trick that I use. Can you picture the cosine graph, like the function, the cosine graph? Okay? What kind of symmetry does that have? Okay. Okay, yeah, the cosine graph is symmetric like this. Okay. Right. What's the name of that kind of symmetry? Do you remember? No, it's even symmetry, okay? Even is split down the center. So for me, I know the cosine graph has even symmetry, and so the cosine polynomial is all the evens. That's just a memory trick that I use, and it works for sine too, because sine has odd symmetry, and therefore sine has all the odd terms. And so the odd polynomials start with u to the first over 1 factorial minus u to the third over 3 factorial plus u to the fifth over 5 factorial minus u to the seventh, etc. And that one, that infinite polynomial, is called a Maclaurin, and it is the approximation for sine. Of course, the longer you go in the polynomial, the more accurate that will be. And then that is the sine graph having odd symmetry. Ooh, that was not good. Okay, and so that's just what I do. So you might want to make a flashcard with the two of those. If you want to do separate ones, you can, but I would usually group those two together. So anytime those pop up in a problem, you can assume that they are representing sine and cosine. It's like memorizing the identity. Sine squared plus cosine squared. Every time you see it, you know that it's equal to 1. So now from now on, anytime you see an even pattern, as long as it's an even pattern with the oscillation of the signs, you know that pattern is going to represent cosine. And the same thing, if you see an odd pattern, that's going to represent sine. Okay, the next two I would group together as well. All right. The next one is 1 plus u squared plus u cubed plus u4 plus u5, etc. We have actually done this one as well. It comes from the model function 1 over 1 minus u. That should make sense to you. Look at 1 over 1 minus u. That's the formula of the summation, right? 1 over 1 minus something. What's the multiplier? U. Okay, it's the ratio. What's the first term? 1. Okay? You can, if you know that this is a geometric series. Okay, this geometric series works out to that geometric sum. We've already learned that. It's also a Maclaurin polynomial centered at 0. So then, in a likewise manner, if you have 1 minus u plus u squared minus u cubed plus u4 minus u to the fifth, etc., what's the multiplier? This is geometric also. Okay, what's the multiplier? Not u. Negative u is the multiplier, so this is 1 over 1 plus u. Alright, so I usually put those two together because they're both geometric.
Does that also mean flashcard?
I would. And I would group them together because they're both geometric series. Alright, the next one. This is 1 plus u squared plus u cubed plus u to the fourth plus ... And you might be thinking, wait a minute, didn't we just do that one? Okay, but I'm going to add denominators. Okay, and the denominators are 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, etc. We've also done this one in a previous example. It's like we're doing them backwards. In the way we did the previous examples, I gave you the function and then you came up with the polynomial. Now, we're saying, okay, here's the polynomial. What's the sum function that it's representing? This one is e to the u. So if it looks like the numerator is geometric, because the numerator is progressing by multiplication of u, powers of u, but the denominator is factorial, that is the exponential model. That gets its own. I don't have a good memory trick to help you with that one. If you think of one, let me know. So the coefficient, so if you're creating it, the coefficient doesn't reduce anything. The denominators stay factorial, 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 factorial. Okay. All right. Next one. Okay. Numerators are u minus u squared plus u cubed minus u to the 4 plus u to the 5. So the numerators oscillate. And the denominators are 1, 2, 3, 4, 5. No factor. That one comes from the natural log function. So we have one of them that generates an exponential function, and one of them that generates a natural log function. One thing about the natural log that is the exception to most Maclaurens are centered at 0, but what would be the problem of doing a natural log centered at 0? It's not even in the domain, right? 0 is not even in the domain of natural log. So for this one, we shift it, we do it 1 plus u. Okay, last one. Only odds. U cubed, u5, u7, u9. Alternating signs. And odd denominators. 1, 3, 5, 7, 9, etc. Okay, this one also, I liked it just because of all the odd things. The graph is a function that also has odd symmetry, and that is inverse tangent. Okay, that's it. These are all found, if you want to reference them again, on page 495 in your book. Like I said, it is not going to be the end of the world if you don't memorize these, but it will save you time if you learn to recognize them so that you don't have to generate them from scratch every single time. So like, for example, they were like, make the Maclaurin polynomial for inverse tangent. Okay, well then you got to go through all the derivatives of inverse tangent. So remember the first derivative of inverse tangent is 1 over 1 plus x squared. Now find the derivative of that. Okay, then again, then again, then again, then again. So I'm just saying this will save you. You can do it, but it will save you time if you have memorized these. Okay. So here's how. You can group them how you want. Like I for sure group the trig ones together, and I group the geometric ones together. The other ones, if you want them separate or together, it's up to you. All right, it's just to drill yourself a little bit. Okay, how is this going to, so those are the facts. Now how are we going to use it? Like what would be a sample problem that you would be asked? Okay. Okay, generate a Maclaurin series A series the same as polynomial because a series is just a sum of individual terms, and so is a polynomial. For the function x squared sine 3x. So we're going to build this. It's like building block pieces that we're going to put together. Let's start with the sine because we have something to model sine. So we know that sine u, based on its odd symmetry, is 1. Okay, can you tell me what it is? We know it's going to have u. Oh, whoops. Starts with u, u cubed, u5, u7, u9, etc. Okay, do the signs alternate? What happens? Okay, so then we've got in sine, we've got the alternating signs. Okay, what else? Okay, the denominators are factorials. So 1 factorial, 3. I started and then I stopped. Okay. Dot, dot, dot. Okay, that's sine u. We need sine 3x. So change all the u's to 3x. Okay, so change all the u's to 3x. So this would be 3x over 1 factorial minus 3x cubed over 3 factorial. So 3 factorial is 6 plus 3x to the 5th over 5 factorial. Does anybody know 5 factorial? 120. Okay. Minus 3x to the 7th over 7 factorial, which we did the other day, 5040. 5040. I don't know 9 factorial, I'll confess. Okay, so there we go, 9 factorial, dot, dot, dot. All right, that's sine 3x. So then how do we make it x squared sine 3x? Distribute an x squared into the whole thing. So x squared sine 3x would be 3x to the 3rd minus 27x to the 5th over 6.
Wait, so are we just kind of like plugging it in as we go?
Yeah, I'm building it. Like I'm starting with the base. My base is the Maclaurin that I know, sine of u.
Yeah, and then you plug in c of x into u.
Right.
And then you add.
And then I multiply x squared so that I. Okay. Okay. 243x to the 7th over 120.
9 factorial is 362,000.
Okay, thanks. Great. So 3 to the 7th, x to the 9th. I don't know what that is. Plus 3 to the 9th, x to the 11th over whatever that is. Dot, dot, dot. Okay, there is my built.
It's not fun.
I am so sorry.
It's okay. Not your fault.
It's our fault.
All right, so, yes, sir.
So will the question specify how many terms do we like how many?
Yeah, they'll give you find the first 4 terms or find the first 5 terms or whatever. Okay, then they also usually say find a general term. Okay. All right, so a general term would be how could you express a sub n? Okay, so let's look at the numerator. Okay, the 3's are going from 3 to the 1st to 3 to the 3rd to 3 to the 5th to 3 to the 7th to 3 to the 9th, etc. So we're going to have 3 to the, is is it 2n minus 1? We need 3 to the
Isn't it odd or odd?
plus 1. Because we need 3 to the first if n is 0. Okay, the x's. Yes, ma'am.
Odd.
Okay, even is 2n. Odd is 2n plus 1. Right, I need my, this is 3 to the first. This is, let me erase it.
Also, the first term is 0.
Yeah, n is 0.
Oh, okay.
It's always 0. It's like ignoring.
Okay, all right, what about the x's? X's are going 3, 5, 7, 9, 11.
2x plus
Okay, 2n plus 3. Okay, and the denominators are 1 factorial, 3 factorial, 5 factorial, 7 factorial, 9 factorial.
No, 2n plus 1.
2n plus 1 factorial.
How are you people getting this?
Because it's a pattern of odds. You just need to know that even numbers are made by 2n's. If you need the numbers to be even, odd numbers are made from 2n plus 1.
Or not just a regular n anymore?
Okay, well, okay, let's go back. N by itself is 1, 2, 3, 4, 5, 6. Okay? If you want to guarantee that you're counting only the even numbers, then you say 2n. Okay, because then that, if you double everything, that will give you 2, 4, 6, 8, 10, 12. Okay. All right, how do you make sure that you, I need to add 0. I need to add 0 because we're starting with 0. Okay, 2n. If we want to guarantee that we are having odd numbers, we need to go one more than all the evens. So then we say 2n, add 1 to all of those. So that would give me 1, 3, 5, 7, 9, 11. So those are our standard rules of counting that help you generate things even versus odd. Okay, if for some reason you would want to start with n to be 1, then you would change this. If n was 1, your 3 would be 2n minus 1. Your x would be 2n plus 1. And this would be 2n minus 1 if you were starting. No, n plus 3 doesn't work because if n is 3, then 3 plus 3 is now 6, which is an even number. Because if you take two odds, and the only way to guarantee odd is to make it even and add an odd number to it.
And since this one's foreign,
Mhm.
so
So we're starting from 0.
you have to do 2.
Yeah, I was just saying if you were making it for a different one.
Okay.
Yeah, so we don't need that. Okay, that is the general plan. So that's most often, like on an FRQ, Ricky, to answer your original question, it'll say, find the first 3 terms and the nth term, or general term, for the following polynomial. And then you would go. And then you would hopefully have that would give you enough to see the pattern, and then you could write an nth term for it.